This video is part 3 of the workflow that we use to fit diode data files from a WITEC instrument. So step 1, we fitted our neon lines, we made a neon line correction model. Step 2, we subdivided our data into groups, where each group has like a distinctive spectral look, so we're going to want to fit it in a different way. And now in step 3, we're going to fit each of those groups. So as normal, load in the Python things you need and load in your information about where the files are, etc. And this is the point at which you load those different groups. So if you remember in the previous video, we actually classified everything in this file as weak. And that's because these were all, none of them had really prominent hot bands that were interfering with the diodes. None of them are going to need a Gaussian elevated background. So for a lot of data sets, you will just have one group. So this then is going to grab the files from that group and it's going to proceed to fit them. So we're going to run through all of this for weak. If you had a second group, you would run through the notebook and then you would come up back to here and you would go through for medium. And you can see that in a later example, but for now, we're just fitting the weak. So what we're going to do is we're going to grab an example file and then we're going to plot it to have a look at it. Okay. And then we are going to tweak the peak fit parameters. So in a similar way to how we did this for neon, we're doing this for our diodes. So we're saying that we're going to fit with a pseudo void peak here. And now we are going to fit various parameters. And you can see here what I've done is I've typed out parameters that work well for weak spectra, medium and strong spectra for our instrument. So I use the same file regardless of what data I'm fitting, whether I'm doing xenolith fluid inclusions or melt inclusion vapor bubbles. Once I've tweaked these for my instruments, I'm pretty much good to go. So what have we got? We've got the model names. This is saying I want to fit a pseudo void peak. This is the best fit that we found. We're saying how many peaks we want to fit. So for the weak ones, we're still going to put 2. We're going to hope that there's a hot band and a peak. If it doesn't find the hot band, in step 2, do you remember we used SciPy find peaks to find the approximate peak positions? If it didn't find a hot band, it's not going to try and fit it. You then want to say the polynomial that you want your background to have. So I'm actually going to set this as a first degree polynomial, so that's going to be a straight line between this background region and this background region. You're going to give an approximate sigma for your diode. So again, this depends on the instrument. Try a value. If it doesn't work and it makes a really narrow peak, you're going to need to make that bigger. It will allow it to look at sigmas within a range, but if you're like miles off, like if your peak sigma is actually 5 and you say 0.6, it's going to struggle with that fit. And then it takes in basically data from this data frame up above that you've loaded in for weak, and this is the approximate peak fit parameters. So the approximate prominence of the diode and the hot band. That was from step 2, and that really, really helps the fitting configuration. So you can see for medium peaks, pretty much the same. The only difference is we're going to use a second degree polynomial instead of a first. And then for the strong peaks, the real difference is we want to fit a Gaussian as well. And this is because the hot bands and the peak are really, really elevated. Just fitting 2 peaks alone doesn't provide good residuals. So you need that additional Gaussian peak. And we discussed this more in the paper and in other examples. It's not really relevant because all of our batches are weak here, so it's only going to be using these top ones. So now we look at the first diode and we see, is this a good fit? So you can see these are the background positions that it's chosen. It's then background subtracted that spectra, and this is the fit. So it's fitted a diode peak and it's fitted a hot band peak. You can see the different peak contributions over here. This is sort of showing that baseline and those peaks in more detail as like a zoomed in diagram. You then have a plot of the residual, so you can see the residual around the peak center is really, really good. It's like less than 10 counts in this region, which relative to the overall peak height of 1400 counts is very, very good. And this is just an overall spectra, and it's going to save this file. So every time you fit peaks, it makes a folder in your Spectra folder with all of these pictures in, so you can go back and look at them. Okay, so we're just going to do the same for diode 2. So you can see, again, we're saying what our model is, what approximate sigma is, and feeding in some of those peak fit parameters. The main difference here is if we had medium, we generally, because diode 2 is much stronger than diode 1, have to fit the Gaussian earlier. So medium spectra typically have a Gaussian for diode 2, but not diode 1. So actually in this case, the medium and the strong are pretty similar. The only difference being, you might need to move your backgrounds a bit because as that peak gets really, really broad, the backgrounds are going to have to move off to the right. Okay, let's fit one of diode 2. So I haven't run it apparently, so we're just gonna go down to here. Okay. So you can see this is our background, this is our peak fits, and this is our residuals. This is all looking good. Like, I'm happy with these fits. So once you're convinced that you're happy, you've tweaked the background positions, you've tweaked the sigma for your Raman, you can then loop through all the files here. So we're going to do this. So it's going to tell you what file it's working on. It's taking about 2 seconds per file. A lot of that time is it to make the figure. So you can see up here you have this plot figure. It's true command. If you set that to false, it's going to be way faster. But then you don't have the figures to look at. So swings and roundabouts. So we're just going to let this go. So here it's just giving me a warning that it's made more than 20 figures. You'll get this if you're using Jupyter. If you're using another Python editor, you might not see this. It's not something to worry about. It's just that it doesn't like us printing a load of figures, but we're going to look at them, so it's fine. We'll live with that. Okay, and now what it's going to do is it's taking a little bit of time. It says it's finished, but it hasn't shown you the results yet. And that's just because it is loading the fits. So you can see this is diode 1 for this file. And then basically what I do is I scroll through them and I'm quickly looking for each image. It takes about a second, that the background position looks good and that the residuals look good and that this fit looks good. So these are all looking good so far. So I'm just slowly scrolling through them. And you're really going to want to do this because if you've got a bad fit, you're going to want to pull it out. You might not trust the data from it. And you can see this is maybe one. This is a C13 peak. So this is maybe one it would have made sense to put in a medium category so that you fit that C13 peak. You can see though that the elevation of this region really isn't too severe. We really don't need our Gaussian yet. So this is still doing a good job of fitting the peak. There's a residual there of about 10 as you tail off out of 3,000. So that's a pretty small residual as things go. So I'm just scrolling through all of these and checking I'm happy with the fits. And I'll write down any ones that I'm not happy with. And then I'm just going to save that parameter. So you can see at combo, that's the name of this data frame. This is all the fits in it. So it's got the splitting, it's got the error on the splitting. This is a really important parameter. It has got this from basically the error, the LM fit, that's the underlying package we're using for peak fitting, gives you for each peak center, propagated them in quadrature. It's got the center position of diode 1, the error on that position. It's got things like the hotband center, the hotband sigma, basically any of the peak fit information is over to here. And you'll see there's a lot of NAND. That's because we didn't fit Gaussian. So we always output the same data frame structure. For strong Spectra, these would be filled in. Anything it didn't find, so it didn't find a C13 peak, it has filled it in with NANDs. Okay, so then if you had medium and strong, you would just go back up to the top now, you would change this to be medium and you would run through, and then it would save that combo down here as medium.diodes, okay? If you're say running a lot of Spectra, you might want to like flick through your phone, procrastinate a bit. You can run this little function here. So this was for when I was using VS Code as my main editor. This will give you a little Windows notification. I'm sure there's ways to do it on Mac, but these kind of things can be useful to implement if, like me, you have a tendency to procrastinate. So what we've done now is we've fitted the Spectra in each group. And then in step 4, we are going to pull all that together. Now there's one final step you might want to do, and that is look for secondary peaks. This is an optional step. This is step 3b. But you can see in this case, we have an SO2 peak. So I would advise watching that video as well. You can go straight to step 4, it'll still work. The only difference is if you ran a step 3b, then you will get that information pulled into your final merge data frame, which has everything in it, including your neon line correction.